Students, welcome back. When we talk about a magnet, we know that a magnet has a quantity called magnetic moment associated with it. And what is magnetic moment? Magnetic moment is equal to the pole strength multiplied by the length of the magnet, and this quantity is called the magnetic moment. And if this is a very short magnet, then we call it a dipole. In that case, if it's a dipole, we call this dipole moment. So this is quite an important quantity, physical quantity, and this can be measured experimentally. Now students, while experimenting with the nucleus, it was found that the nucleus exhibits nuclear magnetic moment, and so this led to the scientists to think how this originated, and they arrived at what is going to be discussed now. So they found that yes, the nucleus has a dipole moment, which they later called it the nuclear magnetic dipole moment. And let us see how this arises. Students, we know that when a charged particle, whenever there is a current flowing in a circular path, suppose like this, in a closed path, suppose a circular path, so this acts like a magnetic dipole. This acts like a magnetic dipole, and so it also has a magnetic moment. It has got a magnetic moment, and that magnetic moment is given by mu is equal to Ia, where I is the current flowing through this circuit, and A is the area of cross section of this circuit. Now again, we know that I is equal to Q by T, and in case of a current flowing through a circular path, this is equal to Q into nu, where nu is the frequency of the circular motion. Now let us look at something else. We know that according to Kepler, for a body or a particle moving in a circular motion, the areal velocity is connected to the angular momentum of the body in this manner. So this is the areal velocity, where A is the area traversed by the particle, and L is the angular momentum. Now let us integrate this equation. When I integrate this side, it is dt, that means we are integrating with respect to time. So let us integrate over a whole cycle, capital T. And obviously when I integrate it, we get this as capital A, and this side becomes this much. So we have I is equal to Q nu and A is equal to this. So let us see how this gives us mu. So we have mu L is equal to Ia. Now I have called it mu L because now let's talk about a particle. Till now we have been talking about a current, circular current flowing through a circuit. Now let's talk about a particle which is moving in its orbit like this. So its orbital angular momentum is L, and so we have mu L is equal to Ia, where I is Q nu and A is this much. So when I use 2 and 4, then we get mu L is equal to this much. We have substituted the values of I and nu, and we got this. Now students, here we have talked about a charged particle. Let us consider the case of a proton, which is inside the nucleus. So for a proton, this same expression, magnetic moment, is written like this actually. So this is this one, here you see we had this q by twice m, and we know that E is the charge on a proton, so this we have written as E, and here we have written this term GL because while deriving this one we have assumed just a charged particle. We have talked nothing about what kind of charge and all these things. So now since we are talking about particles inside the nucleus or subatomic particles, we may also talk about electrons. So we have something called the gyromagnetic ratio, which arises in atomic physics too. So in case of proton, we name in nuclear physics, we call it GL, E by twice m, like this. That means this will differ from particle to particle actually, like this. So we call it like this, and then it was seen that the proton, when the dipole moment of the proton was measured, it was found that there was also a contribution from its spinning motion. We know that the proton spins around its own axis, so it has this one also, so this also arises. So as a result, the proton we have this, the orbital dipole moment and the spin dipole moment, and so we have that the total is this much. Mu is equal to mu n plus mu s, which is equal to, we added them both, we got it like this. So E by twice m was common and we have taken it outside like this. Now for Z protons, can we not write it like this? Because if from one proton I'll have G, suppose I have got a number of protons, so it will have an angular momentum L1, spin S, and a spin S1. For the next one it will be L2 and S2. So things go on like this, so that we will have mu1 plus mu2, so that the total mu can be written in the summation form in this manner. So summation, you see it is going from 1 to Z, because in a particular nucleus there are Z number of protons. So yeah, so this was Z protons. But then it was found very strangely that neutrons also exhibit spin magnetic moment. So that actually was rather surprising, because you see neutrons are chargeless particles, so even if they spin or they move in orbit, they should not give rise to any magnetic moment or any magnetic field or any dipole moment. But then this again drew the attention of scientists towards the constituent of the neutron, and it came to, first of all, they thought that yes, the neutron is made up of two layers, in fact, a central core which is negative, surrounded by positive, like this, so that the effect was of the negative was neutralized by this cloud of positive, but then when the magnetic moment is measured, it shows a negative magnetic moment, which is opposite to the magnetic moment of protons. So they saw this, but then later on, when particle physics developed more and more, they came to the conclusion that neither proton nor neutron are actually truly subatomic particles. They must be composed of some other particles. That's why we see, even though this shows a overall negative charge, it gives rise to a negative magnetic moment. So we'll talk about these things in the last unit, that is elementary particle physics. But for now, it is enough for us to know in this first unit, general properties of the nucleus, is that neutrons also exhibit a magnetic moment which is opposite in direction to that of the protons. Protons have a positive dipole moment, magnetic moment, and neutrons have a negative one. But then neutrons don't show a orbital motion, they only have the spin. So that's why this one this relation, when the neutrons are included, it gets modified to this. So let's see what has happened to in the modification. You see, this talk speaks about the orbital motion, and here we have k going only from 1 to z. But in case of spin, you see, here k is going from 1 to a, because the number of neutrons plus the number of protons gives us a. So we have a spin component for the neutrons and also the protons, and so that we write the sum like this. Now, total angular moment of the nucleus is denoted by this, so that mu is equal to gi into E by twice m, and so this is the total angular momentum, total dipole momentum of a nucleus, which has come from the equation that we have just written in the other page. Now, how is this measured? You know that in case of an atom, the magnetic moment is measured in terms of the Bohr magnet. If you remember, the Bohr magnet is equal to mu b, it is denoted like this, it is equal to E h cross by twice m e. But in case of a nucleus, this is the unit of magnetic moment, magnetic dipole moment, and this is called the nuclear magneton, not magnetron, Bohr magneton, and this you see that the only difference here is, instead of the electron mass, we have the mass of the proton. So obviously, guess which will be greater? Me is small. Since Me is small, so the inverse of Me will be big, so mu b is much bigger than mu capital N. So this is all about the total angular momentum of the nucleus, and this is the magnitude of a nuclear magnetic moment. It's a very small quantity. Here this is minus 27, and here students have missed something actually. Magnetic dipole moment is, when denoted vectorially, there should be this, because angular momentum is like this. So this is like this. So let's go back from the very beginning. Let's come. So we started out here. Here we have like this mu, and this is this, and here we have this like this and like this. This is the area vector. So we have this. Please correct your notes. Here too we have this. No, we will not do this here out here. So we have this, and I'm sure you'll be able to correct everything. Just what I want to prove, my point is that mu L is a vector quantity, and so resulting all of them will be vector quantities. So students, with this we have come to almost to the end of the first unit, general properties of the nucleus. And general properties of the nucleus, this unit is slightly not very interesting, because you have still to know so many things about nuclear forces and elementary particles, and when you learn these things, even this first unit will become interesting to you. So I'll share the study materials of this unit in the Google Classroom.